All right, so we're continuing with section 6, and now we're talking about terminal speed. So suppose the object starting from rest is pushed or pulled by a fluid by a constant force. Initially the speed is low, so the drag force is small, so the net force causes the object to speed up. But drag increases as the speed increases, so eventually the drag force has the same magnitude as F. So now the net force would be 0. So the object is no longer accelerating and is going to maintain the steady speed for as long as that force is applied. That steady speed is called the terminal speed. So it does not have to be in free fall. Usually we associate terminal speed with free fall. If you've ever heard terminal speed before, you think the object is falling, but that's not necessarily the case. It doesn't have to be. In the case of an object being fired at a speed greater than the object's terminal speed, so like in the case of a bullet being fired or something, the very large drag force is greater than the force that's being applied. So then the object would slow until it was moving at the terminal speed. So if you were launched downward at a speed that is greater than your terminal speed, then you would actually slow down until you got to your terminal speed. So the object that's in motion is always going to be trying to get to its terminal speed, whether through speeding up or slowing down, basically is what that's trying to say. So that's terminal speed. All right, so we're going to do a practice problem. We have a 75 kilogram skydiver and his 0.02 kilogram pet mouse are falling after jumping from a plane as shown. Find the terminal speed of each. So we need to figure out a few things here. The coefficient of drag, first of all, I'm just going to give to you. So CD is 1.1.
What does CD stand for again?
Coefficient of drag. All right, now, if I did a balance of forces here, we would have mg down on both of these objects, and then the drag pulling back, so in the upward direction, would be D. So we have D equals mg at the terminal speed. Okay, does that make sense? The weight down equals the drag up when we have reached our terminal speed. Okay, now we have a formula for drag. So drag will turn into 1/2 the coefficient of drag, so CD, times rho, times the cross-section area, times the velocity, and that will be velocity max, squared. So that'll be the terminal speed. And that equals mg now. So I've allowed these objects, the skydiver person and the skydiver mouse, to reach their maximum speed, so that's why I wrote V sub max. So if we're looking for the terminal speed, what am I going to solve for in this equation?
V sub max.
V sub max. Looking for terminal speed, so V sub max. All right, so how am I going to do that? What will I have to do?
Move everything. Divide by everything.
Divide by everything, basically. First, I'll multiply by 2 first, though, because to get rid of that 1/2, that'll be easier. So I'll have 2 mg. And then I'm dividing by C sub D, rho, and A.
And square root in it.
And then I'm going to square root. And that will give me V sub max. Okay, so I know the 2, obviously. The mass, I was given the 75 kilogram skydiver and the 0.02 kilogram pet. I know gravity. I told you the C sub D. Rho would be air that we're falling through, and then the cross-section area we can figure out through the dimensions that they gave us. Now the mouse is given to me in centimeters, so I want to convert that, but we can definitely do both of these problems now. So the cross-section area for the man. Let's figure that out real quick. What will it be?
0.4 times 18 times 4 is 0.72.
0.72?
Yeah.
Okay. Meters squared. And how about the mouse? Remember that's in centimeters, so we want to convert it to meters. So 0.07 meters and 0.03 meters,
21.
0.0021 meters squared. And I can't even use,
Well, that's not right.
I'll use A sub H and A sub M. A sub human and A sub mouse.
Our area.
Or I guess I could use skydiver. That would be good. Skydiver, A sub S. And then mass sub skydiver was 75 kilograms. Mass sub mouse was 0.020 kilograms. Okay, and now all we need is the density of air. So we need to find rho.
Does it matter which one we use? Because we're not at sea level.
Where are we?
Air.
God, it's there. I think it's just,
From a plane.
What do you think?
You jumped out of the plane.
yeah, it's just 1.2.
1.2 what?
Kilograms per.
Kilograms per meter cubed. Okay, so now we know everything we need to know. We can plug all the stuff in. If we take care of the skydiver first, square root 2 skydiver mass 75 kilograms, 9.8 meters per second squared, over 1.1 times the 1.2 kilograms per meters cubed. Oops, I didn't need that. Oh, that's a division symbol, sorry. Okay, and then the cross-section area for the skydiver. All right, calculate it for me.
Goodness. You see goodness.
Can we do like V sub max sub S to show that?
Oh, sure, yeah.
Skydiver.
Yeah, good idea. V for the, let me erase this. I would probably write V sub skydiver max.
Okay.
Smacks.
Are you ready for the answer?
What do you got?
39.328.
So 39.328. And this is velocity, so we should have wound up with meters per second, right?
Yeah.
Yeah.
Okay. Now, what are our significant figures?
3.
I got 75 kilograms. It looks like probably just 2. So I think we're going to go with 39 meters per second. Okay, and we can do the same calculation for the mouse. So that would be V sub M max. Let's see what we get for that one. So 11.89, give me 3 decimal places. 891? Okay. And so even though we had only 2 significant figures, I still like 3 decimal places. It's a good habit. So what is our actual 12 meters per second? Okay. So obviously the man with the 75 kilograms is going to have a much higher terminal velocity.
90, 95, something like that.
Yeah, what's the difference here? The rho, the coefficient of drag. So this number here was the same for both. This number was the same for both. This number was the same for both. So this number here was the same for both. The only things that changed were the mass and the cross-section area, right? So what was the major difference? The mass did change, but also because objects fall at the same rate no matter what for mass, it shouldn't have changed that much, right? But what was the real major difference? The cross-section area. Look at the difference here versus the cross-section area here. That is a massively different number. And that's what really changed the terminal velocity. Okay?
So, hypothetically speaking, if there wasn't such thing as drag, and you were in like, a vacuum chamber and you do this, would something have a terminal velocity? Would that exist?
So there would be no drag if you were in a vacuum chamber and all the air was removed. Drag wouldn't exist at all. So we would be in a strictly free fall, no drag situation. So you wouldn't have to worry about this. It would just be following your kinematic equations with no drag.
So you just keep on accelerating?
You just keep accelerating. Yep. Okay. So now drag at a low Reynolds number. So remember from before, a high Reynolds number means we have an inertial situation where the object is pushing the fluid out of the way. But if we have a low Reynolds number, then we have a viscous situation where the fluid is actually holding the particle up if it's trying to fall, or it's holding it back if it's trying to move forward, okay? So here we have the low Reynolds number situation. So we have a 10, what's this symbol here trying to tell us?
That's the Reynolds number. Wait, no, it's not.
Not what is the Greek letter, it is the symbol trying to tell us the measurement. What is that one? It's not millimeter. It's a prefix for our type of meter, not millimeter. It's not centimeter, it's not a C. It's not a meter.
It's smaller than a millimeter.
Smaller than a millimeter. You would have it in the first sheet that I gave you. I don't remember what color it was. Maybe goldenrod. Micrometer, yeah. And so how far do I got to move the decimal for a micrometer? 6. So it's the next one after millimeter, okay? Millimeter is move the decimal 3. This one says it's 10 to the negative 6th power. So I'm going to move the decimal 6 places. So if I have a 10 micrometer, then it would be 10, and I move the decimal 6 places to the right, okay? So I'm going to go 10. Here's the decimal right now. I'm moving the decimal 1, 2, and then 3, 4, 5, 6. Here's my decimal. That's my number. Okay, so 10 micrometer diameter dust particle settles to the ground at about 20 millimeters per second. So very, very slow. Calculate the Reynolds number. So if I'm doing 20 millimeters per second, I probably got to turn that into meters per second as well. Okay? So how do I turn 20 millimeters per second into meters per second? What do I do? Yeah, millimeters is 1,000 compared to meters, okay? So I'm going to take 20, and here's the decimal right now. I'm going to move that 3 places, so 1, 2, 3, and now I have meters per second. All right. So, how do I do this? What do I do? They want the Reynolds number. So I got to have a formula for Reynolds number. RE equals.
E squared up.
P? It's a P?
Well, no, it's not. It's rho.
It's rho.
Yeah.
It's a special P.
Velocity times
Diameters.
over
They're not square.
using
Over that weird thing.
The weird N is called
Mu,
yeah
or, no, it's called,
mu.
No, it's not. Viscosity, whatever.
eta.
eta. Yeah, it is the viscosity. Okay. So now it's settling to the ground. So what kind of fluid is it in?
Air.
It's air. So we can figure out rho, and we can figure out viscosity. And we are given the velocity, 20 millimeters per second. So we turn that into meters per second. And we're given L, we're given the diameter. So basically we can plug everything in once we figure out the rho and the eta. Okay, so what is the rho? Yep, 1.20 kilograms per meters cubed. Okay, and then we have V. What is that?
0.020 meters per second.
Okay, 0.020 meters per second. And then we have the L. What is that?
That's gonna be
All in
0.020.
All those zeros. I can write that as scientific notation. That would be 1 times 10 to the negative, how many? Fifth meters. Okay, all divided by eta.
Which is 1.8 times
1.8 times 10 to the negative fifth. What are the units on that?
Pascals per second.
Pascals, PA, times seconds, not per second. Pascal seconds. Very strange unit.
Isn't that just, that's newtons, isn't
Pascals are not newtons.
it? It's Newton seconds per meter squared. Right?
A Pascal is what?
Is it Newton per meter squared?
Newton per meter squared. So we have Newton seconds per meter squared up there. Okay, now, does a Reynolds number have a unit attached to it?
No.
No, so all of these units should divide out, right?
Yeah.
Okay, so we're not going to worry about the units. We just got to multiply all the numbers together and then divide by the 1.8 times 10 to the negative fifth. So 0.01 is what you got?
Yeah.
Okay. Yeah, we'll call it 0.01. So here's your answer. Is this a high Reynolds number or a low Reynolds number?
Low.
It's a low Reynolds number, yeah. So that's our guy. Low Reynolds number means that the fluid is holding this particle up rather than the particle pushing the fluid away. And that should make sense. You've seen dust floating around before it settles. It doesn't just fall to the ground. It kind of hangs in the air. So this situation required us to be able to find a low Reynolds number. Okay, so for low Reynolds numbers now, the drag force for motion through a fluid at a speed v is given here. D equals this B now, eta v. Of course, drag is a force that opposes motion, so the direction for drag would be opposite the motion, and so we got that. And then B is a constant that depends on the size and shape of the object. So a lot like the A was the cross-section area, B is just some constant that depends on the size and shape of the object. All right, now, if the object is a sphere, then we're gonna use this formula. So, since we don't know what B is, if we have a sphere, then we can simplify our situation to this guy. So probably this is the guy we're gonna be using.
So if we multiply by 6, that's just how the formula is.
All right, so let's move on and do an example involving pollen grains. They are very light. In one experiment to determine their mass, researchers dropped grains inside a clear glass cylinder and then watched their motion with a microscope. A 40 micrometer diameter pollen grain was observed to fall at a rate of 5.3 centimeters per second. Then, now that we know that, what is the mass in nanograms of this grain? Okay, so
So we don't need to convert that, do we?
what is a nanogram?
Not a gram.
It is a gram. How much?
Small, it's like,
Tiny.
yeah,
Tiny?
0.001 per gram.
So we know milligrams would be 10 to the negative third. We just figured out that micro is 10 to the negative sixth. What's nano?
To the negative 9.
It is 10 to the negative ninth.
I only said that because.
Yeah,
No,
I literally said that.
I'm only saying that because Alexi said it. I'm
Thank you,
pretending to be smart.
All right, good. Credit where it's due. Okay, so obviously this mass is going to be very, very small. So we're going to have it into a unit that makes sense. Okay, so we have 40 micrometer diameter. Let's put that in terms of meters probably. So this would be 40. And then the decimal is here. It will move how many places?
6.
6. So that would be 40 times 10 to the negative 6th meters. Okay, and that is diameter. That's important to note. All right, this is falling at a rate of 5.3 centimeters per second. We want everything in meters, so that would actually be what in meters per second? 0.53?
0.53? Or is it 0.053?
You gotta move it twice.
It's 100 centimeters in a meter, so this would be moved twice. So we have 0.053 meters per second. Any other units we need to change?
Nope.
Okay. So now we have drag force, assuming this is falling at like a terminal velocity. We would have the drag force, D, is in balance with the spherical pollen grain. So that would be 6 pi eta radius
Times 12.
velocity.
The radius, so we have to divide the diameter by 2,
No,
cut it in half.
so it'd just be 1/2 times that in the regular equation.
42.
Now, the drag force actually is going to be set equal to mg, okay? Because down is mg and up is the drag force. Does that make sense?
Yeah.
On a free body diagram? So we have mg equals the drag force, but the drag force is 6 pi eta radius. My etas are looking good today. Velocity.
They really are.
Yeah, I like them.
And now we divide by G.
Yep, we're trying to find the mass, so we're going to divide by g. So we have m equals 6 pi eta r v over g, and we can plug everything in because we know it all. 6 pi, what is eta?
Well, we're in air, so it's gonna be 1.2. Right?
Is it 1.8, 10 to the whatever?
1.8
Oh, yeah.
times 10 to the negative fifth.
We
What are the units on that one?
It's like, yes.
Yeah,
Pascal seconds.
or newtons to the meter squared.
Right. So newtons per meter squared times seconds, right?
Yeah.
Okay. But newtons, so this would be newtons per meter squared, but then times seconds. So newton seconds per meter squared. But a newton is kilograms meters per second squared
So,
times seconds, and then per meter squared. Okay, so all of that is going on right there. Then we have eta. No, that was eta, wasn't it?
no,
That was eta. We need the radius. So the diameter was 40 times 10 to the negative 6 meters. So what's the radius going to be?
Half that.
Half that. What is it?
4.
20 times 10 to the
20 times 10 to the
negative
negative 6th meters. Then
Times the 0.053 meters per second.
Right.
Divided
Okay, meters per second squared.
by, solve for M.
M equals, now all of these units should boil down to just kilograms.
and then we gotta change it to, just wanted to know if I guys could be solving for all of it.
What did you think you were gonna be solving for?
As you're getting that calculation, let's figure out the units. So on the bottom, we have meters per second squared. On the top, we have a meters per second there. So the meters per second will divide out with the meters per second on the bottom and leave me a per second. On the top, up here, we have kilograms. That kilograms better stick around. I don't see any other kilograms, so it's gonna stick around. But I gotta get all these other meters and seconds to go away. So I have up here, kilograms, I have the meters per second squared. I have let's see, a seconds here that's gonna go out. The seconds here will disappear, one of those seconds squared on the bottom. So I just have a seconds on the bottom there. The seconds on the bottom there and the seconds on the bottom will go away. So the seconds are all gone. I have a per meter squared on the bottom there. And I gotta have a meter squared on the top somewhere. Do you see it? There's a meters there. Where's the other meters? Oh, it's right here. The meters squared on top. So the meters squared on top is gone. So all of my meters are gone as well, and I'm left with kilograms. What's my number?
3.6698 times 10 to the negative 11.
So we're gonna call that, since we have two significant figures here, 3.7
Yeah,
times 10
to the negative 11.
to the negative 11th kilograms. Now they wanted nanograms, and we said that nanograms was times 10 to the negative 9th.
So would it just be 10 to the negative second?
So
Negative 20th.
it would move us to, if I move this 2 decimal places, I would have 1 would give me to the negative 10th, 2 would give me to the negative 9th. So 307 D times 10 to the negative 9th kilograms.
20th. Right?
So what's my answer then? Okay, but they said nanograms, not kilograms.
Oh, you divide by kilos.
So I want to move, actually want to move my decimal back a little bit. This would be 370 nanokilograms. I want 300, I want just grams, right? So I actually want to move my decimal back a little bit. How far?
2, 3 places.
0. Oh wait, point
3
370.
places.
Yeah, 3.
3 places.
Point 370. So it's
You're
1,000.
You're going from kilograms to nanograms?
We're going from kilograms, we have times 10 to the negative ninth kilograms.
0 grams.
I actually think we move,
The other way.
we gotta go the other way, right?
370,000.
I wanna turn this into just grams.
Yeah.
It's either 0.370 or 370.
370, 0, 0,
One of the
0,
two.
times 10 to the negative ninth. So
I just
37
don't know.
times 10 to the negative ninth.
Yeah.
Yeah?
Yeah. Let's do so.
Okay, so think of it this way. We have 10 to the, let me just get rid of this here, okay? If we're back here at kilograms, we go 3 decimal places to get to grams, right? Okay. So this 10 to the negative 11th would become 10 to the negative what? 8. So we have now 3.7 times 10 to the negative 8th grams.
I'll shoot it 1.
Okay.
0.37.
Which way do we got to move to get to 10 to the negative 9th?
Negative to the right. The left.
To the right. The decimal wants to go to the left. It wants to go to the left, but we're going to move it to the right to make 10 to the negative 9th, because that's what we need in order to have nanograms. So we're going to make 37 times 10 to the negative 9th grams, and now we have 37 nanograms, and we're done. Okay? All right, last thing, the terminal speed of a styrofoam ball is 15 meters per second. Suppose that styrofoam ball is shot straight down with an initial speed of 30 meters per second. Which velocity graph is correct?
I think this might be one easy.
I eliminated all but D
Yeah.
and E because as you approach your terminal velocity, your acceleration decreases because the drag coefficient is getting greater every time, which means the net force is getting smaller.
So we're told that the terminal speed is 15 meters per second, which means as we keep falling, our speed must get to 15 meters per second. So that rules out A. It rules out B. Even though we get to 15, we keep going past it. So that rules out B. It rules out C because we're going faster and faster as we fall, and we have to approach our terminal speed. And again, it rules out E. So really, the only possible answer is D. We're going faster than our terminal speed. We started off at negative 30 because we're going down. But we must approach our terminal speed. And if actually, calculus would have a good name for this situation right here. Calculus student, what is that?
Hold up. I was zoned out.
You were zoned out. What is this that we're approaching?
Horizontal asymptote.
That's a horizontal asymptote. We are approaching but not crossing. We're getting stuck on that horizontal asymptote right there. That's our terminal speed. So whether we're starting off above or starting off below our terminal speed, so starting off below our terminal speed, we would have the exact same situation. We approach but do not cross our terminal speed. Okay, that's it.